Dear students, our next lecture 2, subspaces. In this lecture, we are going to discuss what is the subspaces of a vector space. Last class we discussed vector space. Now we are going to discuss subspace of a vector space. First, we'll see what is the definition of subspace. Now let V be a vector space. It must be vector space over some field F, and let W some subset of V. W is some subset of V. Then W is called a subspace of V. Then W is called subspace of V. When it's called subspace, it itself is a vector space over F. It's a vector space means last class we discussed vector space. It starts by 9 properties. Means W itself is a vector space with respect to same operations. That operation means vector addition and scalar multiplication on V. What are the general last class we discussed vector addition and scalar multiplication. Those same operations is W also vector space. In any vector space V, this V and 0 itself, the vector space and 0 are subspaces. Are called this subspace is always subspaces. These subspaces are called trivial subspaces, or you can say improper subspaces. Improper. Trivial subspaces are improper. Except this one is called proper subspaces or non-trivial subspaces. Itself is a subspace and 0. This null space. Null space and vector space is always subspaces. These subspaces are called trivial subspaces or improper subspaces. Except those these two, the subspaces are called non-trivial subspaces or proper subspaces. Now some theorem. See, a non-empty subset W of a vector space V over F is a subspace of V. This W is a subspace of V. This if and only if the following conditions are hold. No need to check all those 9 conditions. It's enough to check these conditions for a subspace. For all U comma V belongs to W, but vector addition must be in W. And for all U belongs to W, alpha belongs to field. So alpha dot U belongs to W. This is the vector addition. It's enough to satisfy vector addition. This is scalar multiplication. Scalar multiplication. It starts with vector addition and scalar multiplication. We start with this two conditions. The subspace, this W is called, the subset is called subspace of a vector space. These two conditions, it starts all 9 conditions, that vector addition. It's a closure property and it starts associative property, any vectors. And identity, 0 vector is there, identity, and negative vector also there. And commutative property satisfy. So all these properties satisfy from these two. Or you can write this club of 2, it's enough to check another condition. For all U comma V belongs to W and alpha belongs to club of these two conditions. So alpha dot alpha dot U plus V belongs to W. You check this condition. If suppose this is the one. Okay, check this one. It's checking individual vector addition and scalar multiplication. Sub of vector addition and scalar multiplication. This is the alpha dot U means scalar multiplication. This is alpha dot U. Already we last class we discussed. When you are multiplying a vector with a scalar, again we get vector. Alpha dot U again belongs to a vector space V. Better we are taking W. Alpha dot U again W. That means it's a scalar multiplication. Yeah, again this is the vector. Vector plus vector again vector. This is a vector addition. It's inbuilt. It's this is the club of these two conditions. It's enough to check this condition. Alpha dot U plus V belongs to W. Or you can check individual vector addition and scalar multiplication. The theorem. We'll see some examples. Yeah, I given four examples. We'll discuss some of the example. So now see this first one. Let V equal to R2 over R. This R2 space over field R, and W is the XY belongs to R2. X plus 2y is 0. This is also this condition. Then W is the subspace of V. How to check this one? You can go for two conditions or club of one condition. I will see this one. First example. Okay, now, given V is vector space is the R2 over R, given this one, and W equal to X comma Y belongs to R2, such that X plus 2Y is equal to 0. It's a given. So how to prove it's a subspace? Subspace means it satisfies this condition, this two or this one. Suppose I go for this one, or you can check individual also. I'm checking this club of two conditions. So now let I'm taking U equal to x1 comma y1, then v equal to x2 y2 belongs to w, not w. See, when the two vectors in w means it satisfies this condition. That implies, therefore, when that vector is in w, it satisfies this condition. In place of xy is x1 y1 x2 y2. That means x1 plus 2y1 equal to 0, and x2 plus 2y2 equal to 0. It satisfies this condition. Now you have to check it satisfies vector addition and scalar multiplication. Suppose I'm going to club of two condition. For the field is R, for alpha belongs to R, alpha dot u plus v. Alpha dot u means this x1 y1, v means x2 y2. Alpha dot u, alpha into u is x1 y1 plus v is x2 y2. We know this is alpha x1 y1. This is scalar multiplication. Correct? Alpha x1 comma alpha y plus x2 y2. Suppose take this as one condition. So now sum of two vectors. This again is a vector. This one alpha x1 plus x2, alpha y1 plus y2. This one. This alpha dot u plus v. See now, suppose this vector in belongs to w means it must be such this condition. Now check that one. Now x plus 2y. X plus 2y means first vector. X in place of x is first coordinate. In the first coordinate. In place of x is alpha x1 plus y1. Alpha x1 plus x2 plus 2 into y. In place of y is the second coordinate. That one alpha y1 plus y2. This is equal to, if you take alpha common, x1 plus 2y1 plus x2 plus 2y2. X2 plus 2y2. This one. Now this is equal to alpha into. Now observe from equation x1 plus 2y1 is 0. Plus x2 plus 2y2 also 0. So equal to 0. Correct, from 1. From 1 that one. See. So that means it's this element, it's also the condition, given condition. Therefore alpha dot u plus v belongs to w. Hence w is a subspace. It's also vector addition and scalar multiplication. Hence w is a subspace of R2 over R. This is the way to check subspace or not. It must be satisfied in condition. Now we'll see another problem. Now see second one, where v equal to mn by n r. the set of all square matrices. The vector space is the set of all square matrices, and W equal to A belongs to n by n. A is any matrix that A equal to A transpose. That means set of all symmetric matrices. Set of all symmetric matrices. Then W is a subspace of V. That means set of all symmetric matrices is a subspace. Last class we discussed not only square, any non-square matrix also, it's a form a vector space. M by n matrices. That M by n matrices form a vector space. M by n, it's a square matrix subspace of subset of a M by n matrix. That's why it's also vector space. This V is a vector space. Of we have to check it's a subspace or not. Now we'll see second one. Okay, we'll see that one. See, given V equal to M n by n over R. R means air field is R, and W equal to set of A below any vector M n by n, such that A transpose equal to A, set of all symmetric matrices. So now you have to check. You can go for this condition, R dot U plus V, or you can check individual. Suppose I check individual, the vector addition and scalar multiplication. Suppose let take A comma B belongs to W. When two elements are in W, that implies it satisfies A transpose A and B transpose B. Because when that matrix in W, it's a symmetric matrices only. So now, first condition. Now A plus B transpose. If A plus B transpose is same as A plus B, this A plus B belongs to W. Now A plus B transpose equal to already matrices. That's for this condition. A transpose plus B transpose. This is equal to same as, but we know A transpose equal to A. B transpose equal to B. A plus B transpose same as the A plus B. That means A plus B again symmetric matrix. That implies therefore therefore A plus B belongs to W. That means it starts a vector addition. It starts a vector addition. Now scalar multiplication. Now take for alpha belongs to field R or alpha A transpose. Alpha is a scalar. Alpha transpose, the number transpose again number itself. Alpha A transpose. But alpha A transpose same as A. Alpha A. See, alpha A transpose same as alpha A. Therefore, alpha A belongs. Therefore, alpha A belongs to W. It's also vector addition and scalar multiplication. Hence, W is a subspace of V, where V is Mn by n. Not only set of symmetric matrix. Now you can go for, you can check this is W is skew symmetric matrices. A equal to minus A transpose. This also satisfies traditional scalar multiplication. That means the set of all skew symmetric matrices also subspace of a vector space. So now you can go for this one P2 and another way. This also two subspaces. Already I mentioned is the subspace of B. How to check this one? Now here W equal the given V is P2R. P2R means the polynomial whose degree less than or equal to 2. Set of all polynomials whose degree less than or equal to 2. How to check this one? Take any two polynomials. Just I give idea. You can try this one. Okay. I give idea. This one. Third problem. Let some P of X comma Q of X belongs to W. Okay. Better to mention this. Let P of X equal to some A naught X plus A1X X square A1X plus A2. Second degree polynomial. and q of x equal to b naught x square plus b1 x plus b2 belongs to w. Now you have to, so that it's vector starts with vector addition and scalar multiplication. So it belongs to w. So it belongs to w means, now observe here, it's a w. It starts with this condition a naught plus a1. That means coefficient of x square, sum of coefficient of x square and x is 0. That means that implies a naught plus a1 equal to 0 and b naught plus b1 equal to 0. Now check vector addition and scalar multiplication. Okay, now take for alpha belongs to R, field is R or any R, field R. Now the text color is in a field or check this one alpha p of x club of two condition plus q of x is equal to alpha p of x. P of x means a naught x square plus a1 x plus a2. Q of x b naught x square plus b1 x plus b2. Now simplify this one. Take x square common. This alpha a naught plus b naught x square plus alpha a1 plus b1 x plus alpha a2 plus b2. So now check the conditions. Now the coefficient of x square, sum of coefficient of x square and x, alpha a naught plus b naught plus alpha a1 plus b1. This is equal to, now check this is 0 or not. If take alpha common, a naught plus a1 plus b naught plus b1. We know alpha, suppose if you take this one from 1, this is 0 plus this also 0. You can say from 1 is equal to 0. So this sum of coefficient of x square and x is 0. Therefore, this alpha, therefore alpha p of x plus q of x belongs to w. Therefore, w is a subspace of a vector space P2. P2, this one. Now try that one. Again, this one. Let V be the vector space. Already I explained this total, just to write neatly. You can go for any condition. You can go for club of two condition or individually vector addition and scalar multiplication. Now another problem, let V be the real vector space for all functions. The set of all real functions from R into R. It's already given it's a vector space. Then so that W belongs to be f of minus 1 equal to 0 is the subspace of the, no, it's a subspace. It means the real function at minus 1 is 0. Those functions set this one. It's a subspace. Now you can take, just to give idea, try this one. Let take f comma g belongs to W. If it belongs to W means f of minus 1 equal to 0, f of, sorry, g of minus 1 equal to 0. Now check vector addition and scalar multiplication. That means alpha f plus j of minus 1. This also 0. Then this is the vector space. This is a subspace of B. Now check this condition. Verify it's subspace or not. These are some examples. You can take many examples. You can go check. You can verify any linear algebra book. You are getting plenty of examples. You can try that one. Now another problem. Another examples. Which of the following set of vectors? It's R2 space or subspace of R2. Yeah, which are they are given two W1, W2. Which one is a subspace? Its subspace means it starts the vector addition and scalar multiplication. Suppose it's not a subspace, you can give counter example. Oh, sorry. Suppose it's not a subspace, just to give any counter. You can prove it's not a subspace by counter example or any condition. Suppose you take this one, x1, x2 belongs to R2. It's a subspace means it starts a vector addition and scalar multiplication. Suppose I'm taking first one. Suppose I'm taking by some number. Suppose take 1 comma 2 belongs to W1. Suppose I'm taking this as a vector because R2. So vector addition means you observe here this condition. Uh, suppose -2 belongs to field. So now -2 into 1 comma 2. What about this one? -2 -4. If it belongs to W1, if it belongs to W1, this -2, that x1 quotient must be positive, but here negative. This is not belongs to W. That is a vector. That is scalar multiplication. Scalar multiplication. Not satisfied. Therefore, W1 is not a subspace. This is not a subspace. Now go for this one, second one. Second one also not because x2 is a rational. Suppose for take this one 1 comma 2. Suppose take field. Suppose R2 belongs to R, alpha equal to R2, root 2 or root 3, whatever irrational number. If you multiply scalar multiplication, we will get same example. We will get root 2 into root 2. But here mention x2 is a rational number. 2 comma root is a rational number we are getting. This is not belongs to W2. So this is also not satisfied scalar multiplication. So this one also not a subspace. W2 also not a subspace. These both are not a subspace. Try this problem. You can give any counter example, not only this particular number. You can take anything. Suppose you are taking that. Suppose you want to prove that condition that x1 must be positive number. That is not true always. That's why it's not a subspace. Okay, now see second one. Just to give counter one, anything. Suppose it's not a subspace, just to give counter example. Then which are the following subsets of V or subspaces of V? Given S1, S2, which one is subspaces? So now S1, S1 and S2. Suppose let P of X, yeah, P2R means already you know this is set of all polynomials whose degree less than or equal to 2, not less than 2, less than or equal to 2. Let P of X, generally we take A naught X plus, B naught X plus, sorry, A1X, A2, and Q of X equal to B naught X plus, B1X plus, B2 belongs to S1. Belongs to S1. See, it is, belongs to S1. This is P dash of X. We know that's ordinary derivative. This is sorry, X squared. So 2 A naught X plus B, sorry, A2, A2, A1, sorry, A1. And this one is the Q dash of X equal to 2 B naught X plus B1. It belongs to S1 means it must be satisfied P dash of 1 equal to 0. That implies P dash of 1 equal to 0 means 2A naught plus A1 equal to 0 and Q dash of 1 also 0. That implies 2B0 plus B1 is 0. This is the condition. Suppose you take this is the one. Now check vector addition and scalar multiplication. Now check this one. Alpha P of X plus P of X. If you check this one and differentiate order there, that's alpha P dash of 1 plus Q dash of 1. Suppose this one is 0. That implies alpha P dash of this one term is 0. That implies alpha P of X plus Q of X belongs to W. Sorry, not W, S1. Belongs to S1. Hence, this is the S1 is a subspace. It's satisfied. You can check this condition. Now check this one, S2. You can give any example or another way. Suppose I give a region. You can give any region, not a subspace. Suppose take S2. Yeah, S2 zero polynomial is there. Now you observe here zero polynomial. Zero polynomial is 0 of X is 0. is, yeah, 0 polynomial is equal to 0 polynomial at 0 polynomial at -1. That means a polynomial in this S2 must be satisfied that condition. Yeah, a 0 polynomial also there in this one. 0 polynomial at -1 is 1. Is it possible a 0 polynomial at -1 is 1? 0 polynomial is 0. There is no constant. Only at -1 is no, 1. Not possible. Not possible. Eh, that means it's an all 0 polynomial not possible. That means vector identity is not there. In this one, 0 polynomial is vector identity. But vector identity is not there. That's why it's not a subspace. Vector identity, you can give this region. Vector identity is not there. So it's not a polynomial. Vector identity is not. Okay, you can write this. You can note that. Vector identity is not there. That's why it's not a polynomial. 0 polynomial at -1 is 1. It not is 1 is 1 not possible. That is 0 polynomial is not there in S2. Not right 0 polynomial. Vector identity is not there in S2. Therefore, it's not a subspace. Or you can give another region also. Or you can take by example. Let we'll take x square minus 2x square minus 1. See, now take -1. 2 minus 1 is 1. Let x square minus 1 and another take uh, okay x square. It's okay x square belongs to S2 because these two polynomials are belongs to S2. Because at -1, 2 minus 1, 1. At -1 square is 1. Okay, it belongs to S2, this two polynomial. Now observe here 2x square minus 1 vector addition x square is equal to 3x square minus 1. Yeah, it's a belongs to, is it belongs to S2? See now observe it belongs to S2 means at x equal to -1, it must be 1. But at x equal to -1, 3 -1 square is 1. 3 minus 1, 2. This not belongs to S2. That means it's not such a vector addition. Therefore, S2 is a not a subspace. You can give any one of the reason. You can give 0 polynomial reason or any example. Not only this particular example, you can take any two polynomials. If in S2, tell those polynomials must be in S2. The polynomial in S2 means it satisfies this condition. P of -1 equal to 1. Take those polynomials. Now check vector addition is satisfied or not. If the vector addition satisfies, therefore it's a vector addition and scalar multiplication. It satisfies, it's a subspace. Suppose its vector addition is fail, it's not a subspace. Now we'll see some examples. Suppose I take double one. So this type of example, x, y, z belongs to R3. Not only R3, you can take any space. Suppose some ax plus by plus cz equal to k. When ABC real numbers, a comma b comma c also real numbers. This type of one. When it's a vector space, suppose just like you can, if k not equal to 0 or k equal to 0, then w is a w W1 is a subspace. Always subspace. If k equal to 0, if k equal to 0, that means ax plus by plus cz is 0. That's a plane. Set of all planes. That ABC are any constants, any non-zero numbers, or you can take zero numbers or whatever. Any real numbers. Set of all polynomials, not sorry, set of all subspaces. Sorry, set of all, this is a planes, sorry. The set of all planes, those are passing through origin. It's a subspace. Geometrically, you can check. It's a in a space. Set of all. This is a plane. The passing through origin. It's always a subspace. Suppose set of all players, those are not passing through origin. It's not a subspace. Not passing through origin means the identity vector identity is not possible. So if k not equal to 0, then W1 is not a subspace. You can check it. You can take by example, or you can go for that proof that condition. Take any two vectors and take k equal to 0 condition or k not equal to 0 condition. K equal to 0 condition is satisfied. K not equal to 0 it's not satisfied. Or you can take by counter example. Suppose you take ABC as of particular numbers and you take those numbers satisfy the condition. Now check simply vector addition. Otherwise, suppose I give 2x plus 3y plus or minus z equal to 0. Suppose 2. With 0 it's a vector subspace. You can check it. You take two elements 2x1 to 3y1 z1 equal to 0 and 2x2 3y2 z2 equal to 0 and check vector addition in scalar multiplication. It starts. Suppose it's non-zero. Suppose here 2 is there. Now take any two elements. Satisfy this condition. Suppose two elements means 5. Suppose 1, 1. 3 plus 2, 5. 5 minus 3, 2. Is equal to 5 minus 3, 2. It's in this one. And suppose take another element. 2, 4, 4, 4 minus 3. Suppose minus 1. 4 minus 3, 1. Is it correct? 4, 4 minus 3, 1, 1. Take again minus 1. This belongs to W1. Now observe here, vector addition. Vector addition means if take a vector addition, these two elements vector addition. 1, 1, 3 plus 2 minus 1. This vector addition is 3, 0, 2. Now check, is it satisfied? That means 6, 0, minus 2. 6 minus 2, 4. It's not equal to 2. That means it not belongs to W1. It's not satisfied vector addition. Therefore, when this is non-zero, this is not a subspace. Not only this example, you can take anyone. This type of one you can give counter example when that k non-zero. If it's k equal to 0, you can prove that it's a true for all. In general, it's a true. That's a subspace. When is k is 0? The k non-zero, it's not a subspace. This is useful for entrance exam. But they're given W1 is xyz belongs to R2. They're given 2x plus 3y minus 4z equal to 0. Is it a subspace or not? Of R3. It's true, it's a subspace. Suppose they're given 2x plus 3y minus 4z equal to 2. Is it a subspace? No. Because this is the region, or you can give simple region. You can give simple region. What is the simple region? That suppose this one 2x plus 3y plus 4z, whatever 4z equal to 2. So not because this set is not such for this kind. This is not zero element is not belongs to W1. If it's a zero belongs to W1, this must be such for this condition. Zero belongs not belongs to W1. That means vector identity is not there. That it's not a subspace. You can give any region. You can give this region or by taking any two elements region. Okay. This one of the example. Suppose it's useful for entrance exam. Suppose if you take another W2. Suppose you take W2. Suppose this type of subspace is there. Not only R3. I'm giving R3. Suppose x square plus y square plus z square equal to some k or k square. This one also. Yeah. If k equal to 0, then W2 is subspace. Why it's subspace? Otherwise, not subspace. Otherwise means except k equal to 0, it's not subspace. See, k equal to 0, this x square plus y square plus z equal to 0. K equal to 0. X square plus y square plus z equal to 0. What are the elements satisfied this condition? Only 0, 0 element is satisfied. Means only that means this is the null space only. Null space is always vector space. Therefore, it's a subspace. Suppose k not equal to 0. So suppose x square plus y square plus z square equal to any element, any non-zero. Suppose 1. Is there any element such for this condition? There is no element such for this condition. That's why it's not a subspace. The only k equal to 0 is a subspace. Now we'll see another W3, another one. Suppose to take W3 equal to some another example. Suppose x, y, z belongs to R3. Suppose x plus y is equal to 0. Z equal to k. This also not a k equal to 0, it's a subspace. Not only plus, okay, this one we'll see. This also, if k is 0, subspace, otherwise not subspace. Otherwise, not a subspace. You can give any counter example. Take 1 comma minus 1, 2 comma minus 2. Okay. Z equal to, sorry, 3 elements you have to take. 1 comma, suppose if k is 0, it's a subspace. You can take 2 comma minus 2 comma 0. Suppose take k is 0. When you are adding each elements in W3, if you take vector addition 3 comma minus 3, 0, which is subspace. Suppose k is non-zero. Suppose you take 1 comma 1. Suppose if you take k equal to 1, that means z equal to 1. If you are adding vector addition, we'll get 1 plus 1, 2. But here k equal to 2 we are getting. It's not such a vector addition. It's not a subspace. Now remember one thing. When that given subspace, there is any squaring terms. Squaring terms, any constant term is there. It is not a subspace. Not only constant. Suppose suppose it's a product term also there. Suppose xy is equal to 0. This type term is also there. It's not a subspace. Product, squaring, or constant term, independent of constant term is there. It is not a subspace. Keep in mind, it's useful for entrance exams or any exams. Yeah. Now another some theorem. The intersection of any two subspaces of a vector space is also a subspace. Intersection of any two subspaces. Again, it's a subspace. Whatever you take two subspace, the intersection is again subspace. And this proof is simple. Just to give idea. Suppose let W1 comma W2 be two subspaces of a vector space V. Yeah, two subspaces of a vector space V. Yes, subspaces means it's containing identity. Therefore, zero vector. This zero vector belongs to W1 comma W2. That implies 0 belongs to W1 intersection W2. That is W1 intersection W2 is non-zero, non-empty set. Is non-empty. Not equal to 0 or is non-empty. Is non-empty. Non-empty set. Now you have to prove it's a subspace. Intersection is subspace. Suppose let U comma V belongs to W1 intersection W2. I'm taking two vectors in W1 plus intersection W2. That means you have to prove vector addition and scalar multiplication must be in W1 intersection W2. That implies when the two vectors in W1 intersection W2 means U comma V belongs to W1 and U comma V belongs to W2. See, W1, W2, two subspaces. Its subspaces means it starts by vector addition. Alpha U plus V belongs to W1 and alpha U plus V belongs to W2. For alpha belongs to any field. Okay, take here field F for alpha belongs to F. Now you have to, yeah. Now observe here, alpha u plus V belongs to W1 and alpha u belongs to V W belongs to W. Yeah, therefore, alpha u belongs to V belongs to, okay, correct. That implies alpha u belongs to V W1 and alpha. That implies alpha u plus V belongs to W1 intersection W2. So now observe here, see, we have taken u comma V belongs to intersection. That we are getting that vector addition and scalar multiplication again in intersection. Therefore, W1 intersection W2 is a subspace. Okay. Not only any two subspaces, it's take arbitrary intersection also subspace. Not only two, three, four, whatever arbitrary intersection of arbitrary subspaces. Again, it's a subspace. This one. Now, what about union? Suppose take example. Suppose what about union? It's an intersection is subspace. Union. Suppose I've taken W1 is 0 by 0 belongs to R3. This one. And suppose I've taken W2 equal to such that Y belongs to R. Suppose taken 0 Y comma Z, which belongs to R3, such that Y comma Z belongs to real numbers. Take X also, better. X. Now, suppose it's a subspace means it's a must satisfy vector addition and scalar multiplication. Suppose we know this is W1 union W2. What the W1 union W2 mean? X comma Y 0 union 0 Y Z. Such that X Y Z belongs to R. Okay. This is the set. Suppose take 1 comma 2 0 and 0 1 3. So it belongs to W1 union W2. So it's a subspace. It must be satisfied vector addition. Nothing but now what about vector addition? 1 2 0 plus 0 1 3 is equal to vector addition 1 comma 3 comma 3. 1 comma 3 comma 3 is this element in W1 union W2? In W1 union W2, either elements to non-zero and 0 are to non-zero. But three non-zero elements is non-zero elements is not there. First coordinate, second, third. All are must be either last one 0 or first one 0. This is not satisfied vector addition. Not satisfied vector addition. Okay, better take a x1, y1. Two different one. Take x2, y2, y2, z2. So two different one. That's why I'm writing x1, y1, y2, z belongs to R. All are different elements. Whatever you can take same elements also no problem. Just not such a vector addition. Therefore, it's not a subspace. Therefore, union is therefore W1 union W2 is not a subspace. But intersection is always subspace. But union is not subspace. And when it's subspace, we'll see this theorem. The union of two subspaces is a subspace if and only if one is contained in the other set. That means that is if and only if condition. If W1 for if W1 union W2 or that statement, if W1 union W2 is a subspace of vector space V over F, if and only if one is contained the other, or W2 contains W1. One is contained the other. In this case, it's subspace. You can check this proof, or you can go for this one. This if and only if condition. You can verify any book, it's available. Otherwise, if you want interested, you can ask me personally, or you can ask in doubt session. Anyway, we are not asking in exam. We are not asking proofs in exams. Just application we are asking. Okay, I give counter example this one. Suppose if you take example, I can give. Suppose take W1 equal to x comma y 0. It's such that x comma y belongs to R. And suppose if you take x1 y1 and W2 equal to x2 comma, okay, 0 comma 0. Okay, take simple example such that x2 belongs to this one. Now observe, now W1 union W2. What is the W1 union W2? This is x1 comma y1 comma 0 union x2 comma 0 0. Such that x1 y1 x2 belongs to this one. Now check vector addition. Whatever vector addition, two elements. Okay, take directly. Now vector addition x1 y1 0 plus whatever you take elements. Suppose I'm taking okay, directly this example x2 0 0. This is equal to, we get x1 plus x2 y2 0. 0 belongs to W1 union W2. See, now x1 is a real number. X1, x2 real number. X1 plus x2 also real number. Y2 also real number. It's like this type of element. It belongs to W1 union W2. It's also a vector addition. Not only, you can take scalar multiplication. If you take alpha into this one, alpha x1, alpha y1, we are getting alpha x1 plus x2, alpha y2. This alpha is a real number. Alpha x1 plus x2 also real number. This also real number. It's a vector addition and scalar multiplication. So it's a subspace. Why it's subspace? Now observe here, we are taking W1 and W2. Observe here, W2 is contained in W1. W2 is contained in W1. That's why it's a subspace. Otherwise, it's not a subspace. Or it must be W1 subspace, either containing W1, W2 containing W1 or W1 containing W2. In this case, only it's a subspace union. Otherwise, it's not a subspace. So for this one, W2 is containing W1. That's why it satisfies vector addition and scalar multiplication. Okay, now you can use this condition. This is alpha x1, alpha y2. This is belongs to W1 union W2. Therefore, it's a subspace. Subspace. Okay. Union is not a subspace always, but it's one containing the other one. Now I stop here. Write problems on subspaces. I will write some problems on PDF file. Okay, thank you.